This is the last tutorial in the section of cellular automata as for the date of September 2023. Here we're going to extend the concept of emergence a little bit because we start merging into some other domains in computer science algorithms. We're going to be looking at the idea of generating a path that connects a given tile, if possible, with a destination tile, which is going to be the target. You can think about it as solving a maze. So here we have two different types of tiles in our two-dimensional grid system. You have the black ones, which represent walls, and you have the white ones, which represent the path or empty areas in which any object like particles eventually emerge and start trying to find its path somewhere, trying to solve that maze. This green tile right here is going to be the destination tile. It's just another tile with the state white, and what it has special is that this is going to be the tile that starts everything. The algorithm that we will implement combines a little bit of cellular automata with the concept of breadth-first search. The concept of breadth-first search relies on the idea of first finding everything that surrounds this green tile here and then appending it to what is known as a stack. Before I get too ahead of myself, I also need to tell you that the way we will represent this two-dimensional grid is by the use of strings. In particular, we are going to use a list that will include all of these rows, representing each of the 4 different rows in our grid system. The identity of each of the tiles states is given by a binary number, and all of them have been casted inside of strings. We do this for simplicity. We're going to use this information later to determine which state we should give at the beginning of the animation to each of the different tiles. So let's talk about how this algorithm works. We are going to start by first appending this green tile that starts everything to a special list called the stack. The stack is a sequence, ordered sequence, that is, of the tiles in the same order in which we find them as we explore the map. So, in this algorithm, we're going to count 4 different neighbors if we are within the boundaries of the grid and if such neighbors are not walls. In this particular case, we only have one neighbor, which is down. What we're going to do is to append this orange neighbor right here into the stack. And now that it is into the stack, we're going to change a parameter inside of this tile called visited from false to true. That way we have marked the tile so that the next tiles that we explore are not going to go back and think that this tile right here is something that we haven't explored yet. So there it is. Before we proceed, we're also going to make sure that we register the direction in which the previous tile came from. In this case, this orange tile should be pointing in the direction up. Before we leave this iteration in the algorithm, we get rid of the first element in the stack, and then that will make the second element in the stack the new element. Now, we can focus on the next neighbors. We start with this one, and we can evaluate how many neighbors it has. In this case, it only has 1. Remember that this one has already been visited. Then we repeat the process over and over again. And the pattern we're going to end up with is a series of lines that are going to connect each of the tiles with the green tile that represents the destination. There is a really good series of tutorials from Amit Patel. So I have left the link in the description of this tutorial in my own webpage. I encourage you to look into the different tutorials that he has, as they are really comprehensive. The one we're going to be looking at is this one right here. It's known as the flow field pathfinding. In addition, it also includes some interactivity so that you can generate some interesting behaviors if you just want to explore the algorithm in real time. So let's get started with the implementation of this algorithm so that we can visualize a path.